In the quiet of a dusty laboratory in 1797, a man stood before a pair of lead spheres suspended by wires and silence. He wasn't building a weapon or discovering a new planet. He was trying to do something far more bizarre. He was trying to weigh the Earth, not with a scale or by digging into its crust, but by measuring the subtle dance of gravity itself right there in his room. No rockets, no satellites, just wires, weights, and patience. This is the story of Henry Cavendish, the man who uncovered the invisible force that holds the universe together and measured one of the most elusive numbers in all of physics, the gravitational constant, G. To understand why this was such a monumental feat, we need to step back and consider what gravity actually is. For centuries, gravity was a mystery. People knew that apples fell and the moon orbited the Earth, but no one truly understood how or why. Then came Isaac Newton. In 1687, Newton published his Philosophia Naturalis Principia Mathematica, where he described gravity as a force between any two masses. The bigger the mass and the closer the distance, the stronger the force. But while Newton gave us the equation F equals Gx m1 x m2 r2, he left a key part unknown, the value of G, the gravitational constant. That tiny number, that mysterious multiplier, was what turned a mathematical relationship into a measurable force. Without knowing G, Newton's law couldn't be used to calculate actual values. It was like having a recipe without the measurements. No one knew how to measure it, not for over a century. Then came Cavendish. Henry Cavendish was a wealthy, reclusive Englishman with a deep obsession for scientific precision. He spoke little, avoided social events, and rarely published his findings. But he was a genius of the highest order, meticulous, patient, and brilliant. His goal was deceptively simple: to measure the mass of the Earth. But to do that, he needed to measure the strength of gravity between two small objects in the lab, something no one had done before. Why? Because gravity is incredibly weak compared to other forces. You can pick up a paperclip with a fridge magnet, overcoming the gravitational pull of the entire Earth. So how do you measure the gravitational attraction between two lead spheres in a room? Cavendish used an ingenious device called a torsion balance. It consisted of a lightweight wooden rod suspended horizontally from a thin wire. On each end of the rod, he attached small lead spheres. Then he positioned two much larger lead spheres nearby, but not touching. Gravity would cause the smaller spheres to be ever so slightly attracted to the larger ones. This pull would twist the wire, rotating the rod. The twist was minuscule, but Cavendish, with extraordinary care, measured it using telescopes placed outside the room, peering in through windows to avoid disturbing the air inside. He waited for hours, days, sometimes weeks, just to allow the system to settle. Then he recorded how much the rod turned. That angle told him how much gravitational force was acting between the masses. From that, he calculated the value of G. Today, the accepted value of G is 6.674 sestan 10 to 11 m3 so key s2. Cavendish got astonishingly close, especially considering he was working with 18th century tools. He didn't technically refer to it as G, that would come later, but the implications of his measurement were clear. With this constant, you could now plug in the masses of two objects, their distance apart, and calculate the force of gravity between them. But more importantly, you could determine the mass of the Earth. And that's exactly what Cavendish did. Using his measurement of G and Newton's formula, Cavendish calculated Earth's density, and from that, its mass. It was the first time in human history that anyone had successfully weighed the planet. No need for global surveys or seismic analysis, just pure thought, a clever instrument, and a whole lot of patience. This is why Cavendish's experiment is often mischaracterized. People say he measured G, others say he measured Earth's mass. In truth, he did both. But his work went even further. By confirming that two small spheres could attract each other measurably, Cavendish proved something profound, that gravity is universal, not just something large bodies like Earth or the Sun produce. It acts between everything, no matter how small. A teaspoon and a grain of sand are pulling on each other right now. You and your chair, the walls around you. Every atom in your body is gravitationally interacting with every other atom in the universe. Cavendish made that visible. Of course, his method wasn't perfect. Measuring G is notoriously difficult, even today. It's the least precisely known of the fundamental constants. Over the years, scientists have tried dropping weights down holes, swinging pendulums, and using vacuum chambers to refine the number. But it's still frustratingly hard to pin down. Even in the 21st century, G is known only to 4 or 5 significant figures. Compare that to the speed of light, which we know to over 10 decimal places. Why is G so elusive? Because gravity is weak. Not in the sense of being unimportant. It shapes galaxies, bends light, and governs the structure of the universe. But compared to the electromagnetic force or the strong nuclear force, gravity is feeble. And that makes it hard to isolate, measure, and study. Cavendish's genius was in designing an experiment so sensitive that it could detect this tiny tug between masses. His lab became a temple of patience where gravity whispered its secrets. And yet, the man himself remained a mystery. Cavendish published little. He avoided fame. Much of his work was discovered posthumously, buried in notebooks that revealed he had beaten others to discoveries by decades, like Ohm's law and the composition of air. But his experiment remains a towering achievement, a demonstration that, even without modern tools, the universe can be understood with careful observation and relentless curiosity. The balance he used sits today in a museum, revered not just for what it measured, but for what it represents, the power of human thought to weigh the world. And all of it began with 2 lead balls, gently pulling on each other in the stillness of a room. But this was just the beginning. Because once you can measure gravity on Earth, you can start asking deeper questions. How does gravity really work? What is it exactly? Why is G so small? And does it stay constant across the universe or across time? The quest to understand gravity has led us from Cavendish's quiet lab to the warped space-time of Einstein, the fabric of general relativity, and the strange possibility that gravity may not be a force at all, but a geometric distortion. It's a journey that continues today. Because behind that tiny twist of wire was a question that still haunts physics. What is gravity? And the deeper we look, the stranger it gets. When Cavendish measured the gravitational attraction between 2 lead spheres, he wasn't just weighing the Earth, he was opening a door to a hidden layer of reality. That thin wire, twisting ever so slightly, revealed a force that connects everything. But what exactly is gravity? And why does it behave the way it does? For centuries, gravity was simply accepted as a fact of nature. Newton described it as a force between masses. The larger the mass, the stronger the pull. The farther apart the objects, the weaker the force. His law worked beautifully, predicting everything from falling apples to planetary orbits. But it didn't explain what gravity was. It only described how it behaved. That explanation wouldn't come until 1915, when Albert Einstein introduced his revolutionary theory of general relativity. Einstein saw gravity not as a force, but as a curvature of space-time. Imagine placing a heavy bowling ball on a trampoline. It bends the fabric, creating a dip. Now roll a marble near it. The marble doesn't get pulled by the bowling ball, it rolls into the curve. That's gravity in Einstein's universe. Mass tells space-time how to curve, and curved space-time tells objects how to move. This idea turned our understanding of gravity upside down. Suddenly, it wasn't just about masses and distances, it was about a geometry, about how space and time are shaped by matter. Light could bend, time could slow down. Even the path of a planet could shift if space itself was warped. But if gravity is the bending of space-time, What exactly is g doing in our equations? Einstein's equations contain a version of g too. In his field equations, g appears as the proportionality constant that links the geometry of space-time to the distribution of mass and energy. It's the bridge between the shape of the universe and what's inside it. But here's the strange part. G doesn't emerge from deeper theory. It's not derived from first principles. It's measured, just like Cavendish did it. That makes it a fundamental constant and one of the biggest mysteries in physics. Physicists have long wondered, why is G so small? Compared to the other fundamental forces in nature, gravity is absurdly weak. The electromagnetic force is about 1036 times stronger than gravity. That's a trillion times. So why is gravity so feeble? There's no agreed upon answer. Some theorists suggest that gravity might be leaking into extra dimensions, hidden spatial directions that we can't perceive. In this view, gravity is just as strong as other forces, but its strength is diluted because it spreads out into a larger space. Others believe that G's smallness is simply a key cosmic coincidence, one of the many finely tuned numbers that allow life to exist. Either way, this weakness is what makes gravity both hard to study and more deeply fascinating. Cavendish's experiment by revealing G gave us the key to weigh planets, understand tides, model galaxies, and even build GPS systems. But it also introduced a new layer of complexity, because once you know how to measure gravity, you can start to see its strange behavior everywhere. Take, for example, the gravitational constant problem. You might think that a constant like G should be, well, constant. But when scientists measure G using different methods, they sometimes get slightly different results. Not wildly different, but enough to raise eyebrows. Could G be changing over time? Is it different in other regions of space? These are not just theoretical questions. They're being actively investigated. If G is truly variable, it could point to new physics beyond Einstein and Newton. It could mean that our current models are only approximations of a deeper reality. But even with our best instruments, G remains slippery. Unlike other constants, like the speed of light, which is defined exactly, G must be measured over and over, and it stubbornly resists precision. That's why experiments like Cavendish's are still being repeated today, with lasers, vacuum chambers, and superconductors. In 2018, two teams using different methods both measured G to unprecedented precision and got different results. That sparked debate in the physics community. Some called it the crisis in G, others saw it as an opportunity. Maybe we're missing something fundamental. Maybe gravity is pointing us toward a deeper layer of nature. But gravity doesn't just act on planets and stars. It shapes you. Your body, your bones, your blood, they all obey gravity. If you stood on a different planet, your weight would change, your muscles would adjust, your entire physiology would be altered. Gravity influences how life evolves, how blood flows, even how we think about up and down. Without gravity, there would be no atmosphere, no oceans, no stars, no life. It is the quiet architect of the universe, and yet we still don't fully understand it. Which brings us back to Cavendish. In his lonely lab, he wasn't just spinning wires. He was capturing a thread of the cosmic web. He gave us a number, but also a question that has haunted physics ever since. What is gravity really? Einstein gave us curvature. Newton gave us force. Cavendish gave us measurement. But none of them gave us the final answer. Some physicists today believe that gravity isn't fundamental at all, that it might emerge from something deeper, like entanglement, information, or quantum geometry. The idea is called emergent gravity, and it's one of the leading frontiers in theoretical physics. Others are hunting for the graviton, a hypothetical particle that would carry the gravitational force, much like photons carry light. But despite decades of searching, no one has found a graviton. And perhaps we never will. Maybe gravity can't be quantized. Maybe it exists outside the framework of particles. Then there's the ultimate challenge, unifying gravity with quantum mechanics. Right now, physics has two main pillars: general relativity, which describes the cosmos, and quantum field theory, which describes the microscopic world. Both are wildly successful. Both have passed every test, but they don't fit together. Gravity refuses to be quantized. Quantum mechanics refuses to accept curves in space-time. They speak different languages. That's why physicists dream of a theory of everything. A single framework that can describe black holes and electrons, galaxies and quarks. String theory, loop quantum gravity, and other exotic ideas are all attempts to bridge this divide. But so far, gravity holds its secrets. And G, the number Cavendish measured in 1797, remains at the center of the mystery. It connects every apple to the Earth, every planet to its star, every galaxy to the cosmic web. And it reminds us that the universe is not just made of matter, but of relationships, of invisible threads pulling and bending and curving space itself. That's what makes gravity so strange. It's the weakest of forces, and yet it dominates the universe. It's everywhere, and yet impossible to pin down. It can crush stars, and yet be measured in a quiet room by a single man watching two lead balls gently move. The experiment of Cavendish is a story of measurement, but also of wonder, of how even the smallest twist in a wire can echo across the cosmos, and of how the weight of the Earth is nothing compared to the weight of the question behind it. If gravity is so weak, why does it dominate the universe? Why is it the force that governs stars, galaxies, and the fate of everything we see? That question leads us to one of the most profound realizations in physics. Gravity may be weak, but it's relentless, always attractive, and it operates over infinite distances. And this makes it the great sculptor of the cosmos. Think of the early universe. Just after the Big Bang, matter was almost evenly spread across space. There were no stars, no galaxies, just a hot, dense soup of particles. But gravity doesn't tolerate perfect balance. Tiny fluctuations, just quantum jitters, were enough for gravity to get to work. Denser regions began pulling more matter toward them. Over billions of years, these ripples grew into stars, galaxies, and superclusters. No other force could do this. The strong nuclear force holds atomic nuclei together, but only over tiny distances. The weak nuclear force governs radioactive decay, and the electromagnetic force is powerful, but it can repel as well as attract. Only gravity keeps building, always pulling in, never pushing out. And this is where Cavendish's constant G plays a key role. Even though G is small, it's the scaling factor for all gravitational interactions. Without it, you can't model planetary motion, launch spacecraft, or even predict tides. G sets the strength of the pull. But it also raises a cosmic tension. The universe should be collapsing under its own gravity. So why isn't it? This question baffled scientists for decades, until 1998, when astronomers studying distant supernovae made a shocking discovery. The universe isn't just expanding, it's accelerating. Some unseen force is pushing everything apart faster and faster over time. That force has a name: dark energy. And suddenly, gravity wasn't the only player on the field. Something was working against it. In Einstein's original equations, he had added a term called the cosmological constant, a mathematical tweak to allow for a static universe. Later, he called it his greatest blunder, because we discovered the universe is expanding. But now that term has returned. Dark energy may be nothing more than a cosmological constant, something built into the fabric of space-time that causes it to stretch. And here's the weirdest part. Dark energy makes up about 70% of the universe. Dark matter, another invisible substance that interacts through gravity, makes up about 25%. That leaves normal matter, everything we can see, as just 5%. Gravity, as it turns out, is both our guide and our blindfold. It lets us detect what we cannot see. We know dark matter exists because of how galaxies rotate and how light bends through gravitational lensing. We see its fingerprints, but not the substance itself. And again, we need G to make sense of it all. Every time we observe a star orbiting too fast or a galaxy being warped by invisible mass, we're using Newton's law, F equals G x m1 x m2 r2, to infer what must be there. Cavendish's constant is the key to seeing the invisible. But is G really constant? Some modern theories suggest it might not be. In models where extra dimensions exist, like in taut string theory, gravity could be diluted across higher dimensional space. In others, G may vary over time or across cosmic distances. If true, this would rewrite our understanding of cosmology, of structure formation, and even of the eventual fate of the universe. Some physicists are now testing whether gravitational interactions behave differently at extreme scales, like near black holes or in the early universe. They're probing the edges of relativity, looking for deviations that might point to a deeper theory. And one of the places they're looking is in the gravitational wave spectrum. In 2015, the LIGO Observatory made history by detecting gravitational waves, tiny ripples in space-time caused by colliding black holes over 1 billion light-years away. These waves confirmed a prediction of Einstein's theory, and they opened a new window into the cosmos. What's striking is that even these enormous events, black holes with dozens of solar masses, only produce waves that stretch space-time by less than the width of a proton. Gravity, again, is subtle. But now we can listen to the universe through these tremors. We're measuring the cosmos in vibrations, using instruments so sensitive they can detect changes smaller than atomic nuclei. Gravitational waves are the ultimate proof that space-time is not static, it's dynamic. It can ripple, flex, and carry energy. And through those waves, we're learning about black holes, neutron stars, and the fabric of the universe itself. But there's another twist. If gravity can ripple, then what else can it do? Could it tunnel? Could it fluctuate? Could it, under extreme conditions, break down? Physicists are pushing to find out. They're building larger detectors, sending missions into space like LISA, the Laser Interferometer Space Antenna, to catch waves from even more distant and massive objects. And through it all, Cavendish's constant remains at the core. G is everywhere, in every calculation, in every simulation of the early universe, every model of black hole mergers, every orbit plotted by space agencies. But it's also a mystery. Where does it come from? Why is it so small? Could it be changing? Is it connected to other constants, like the Planck constant or the speed of light, in some hidden way? Some theorists think we're close to a breakthrough. That gravity might emerge from entropic forces, from thermodynamics, or from the information content of space-time. The idea here is radical, that gravity isn't a fundamental interaction, but a statistical phenomenon, a byproduct of deeper, microscopic processes. In this view, space-time itself might be made of discrete units like pixels in a screen. Gravity would then arise from how those pixels interact. G, in this case, would be a kind of conversion factor between our macroscopic experience of space and the underlying quantum code of reality. We don't know if that's true, but the fact that physicists are entertaining such ideas shows how much gravity still baffles us, even after centuries of study, and even after one man in a quiet lab measured the weight of the world using spheres of lead. So where do we go from here? We keep measuring. We keep listening to the cosmos. We keep building better instruments. And we keep asking the question Cavendish couldn't answer. Not just, how much does gravity pull? But, why? Because in the end, G isn't just a number. It's a riddle, one that might take another century or another Einstein to solve.